Hey guys, this is JSer. How's everything going? In this video, I'm going to take a look at 315, count of smaller numbers after self. We're given an integer array, and I have to return a new count array. The count array has a property where each element is the number of smaller elements to the right of itself. Like 5261, we need to return 2 because there's 2, 1 right after 5 and a smaller than 5. For 2, there's 1, right? Only 1 smaller than it. And 6, only 1 smaller than it, and then for 1 there's nothing smaller than it, so 2110. So well, if we do it brute force, it actually need to loop through for 5 3 elements, for 2 elements, so obviously it's quadratic. So how could we improve it? Well, let's analyze the example. For 5, we need to count 2, 6, 1, right? And for 2, we need to count 6, 1. So there's a duplicate, 6, 1. So what about we think about the reversely? So for 6, we check 1, and for 2, we check 1, 6. For 5, we check 1, 6, 2. So in each iteration, we only need to add 1 to the previously checked numbers set, right? So what if there is some data structure in the checked numbers, and we can get that faster than a linear time? Well, the first idea comes to my mind is that what about a sort? So from right to left, we check, okay, 1, and then 6 bigger than 1, okay, and then so bigger than 1, so for 6 there will be one number, right? And for 2, well, this is sorted. So to check how many numbers are there smaller than 2, of course we use binary search. We search it and find that it's only one number smaller than it, and then insert 2 in it, and then it got 5. Again, we use binary search and find that 2 numbers smaller than 5 and insert it. So by this, we for each number, we will cost us logN to find how many numbers are there, and we insert it. But there is a pitfall here. To the insertion actually costs time. We need to shift the index for array. So actually it still costs linear time. I would say it's cost and yeah, still quadratic. So what's the structure that maintains we can do binary search and do insertion with the constant time? Could you do that? If we do binary search, I cannot think of anything. If linked list, if we could insert with constant time. Priority queue, insert is logN. There's something other thing. If priority queue, we cannot. We only know which one is the smallest or the largest, so cannot improve that. yeah, I'm stuck here. So anyway, allow me to implement this binary search implementation. Okay, so of course we need to keep track of the result, right? The last number, there's nothing right after it, so it's 0. We push it and finally reverse the result because insertion will cost more time. And we will maintain a sorted list and put the last numbers in. And now we will insert find the insertion position for each number. We'll use binary search here. Start equals 0, end equals sorted, .nest -1. So typical binary search thing. If sorted, the middle one is bigger or equal to start, the number, then there might be some numbers smaller than it to the left, right? So we in, if not, start +1. After this search, start is the insertion position. Then the number is smaller than it. Actually, is start itself because it's 0 base. Insertion at 2 actually means there's a 2 number smaller than it. So result push start, and we will do the insertion, which is sorted, a splice, start, 0, and none. And, yeah, and finally we return the result to reverse. So the core problem is this one actually. These cost us linear time. Internally, could it be a linked list? No, it's impossible. So these cost linear time. Sad. Anyway, for time it is square. Not good, man. Space is linear. We use extra sorted array. So this is the best I can do. Yeah, what's the any other structure that we could do? Insertion with logN, right? If we can do insertion with logN, binary search, we're going to shift the index. The other linked list, we cannot do new binary search. And priority queue, we cannot do binary search. What about binary search tree? Binary search tree. Binary search tree, do the search will cost log n, and the insertion would be like linked list. Oh yeah, I think we could possibly improved with the BST, because for the search, well, that depends how you organize your BST, right? If you just loop through the numbers from right to left, for the worst case, it's still quadratic time. because you will have a flattened linked list. You search will cost you a linear time. Maybe you can shuffle the array first, possibly improve with BST with n log n to n square. Well, if you need some follow-up, you can mention this and start working on it. And shall we do it here? What? 10 minutes? Okay, allow me to have a try. Okay, for the BST, I'll create a node, right? Class node structure val. For the node, it will have the val, and when we do insert, we step on the node. If bigger than it, we go to the right, right? Go to the right, then we need to know how many numbers are smaller than it. So this val is val, this count of smaller than it equals to 0. Yeah, this is a node, and there is BST, right? So this left equals null, this right equals null. Okay, so now count smaller for nums. Okay, we create a root new node which is nums. Okay, I think we should choose. What if there's duplicates? Like duplicates, then we just count, right? Bigger than it or equal to it, smaller. And okay, there is count of smaller, is count of cell equals 1. We use the last number as a root. Okay, node nums.length minus 1. Okay, this is the root. Now we will create a function called insert. Okay, search and insert, which accepts a node, which will return the smaller numbers. How should we do it? So let's start p equals root. Okay, we'll compare this p to node. While p, the next position, right? The next position, if it's null, I think we should use recursion, or check the nodes and check the nodes against the target value. If it's bigger, then we will go to the next node. But if there's nothing there, we break. Okay, we use while loop. So okay, so while p, then we compare the node val. Node val, if it is equal to, if node val is equal to the p val, then we should break, right? We found the insertion position, and we need to increment the not node val, but p val. Well, p count of self plus 1. And we return, okay, there's no need to break. We just return it. P count self. Oh, just return the count of smaller. Yeah, that's it. And so this is not the same. So if p's val is bigger, not p val, but oh, the node val actually. Node val is equal to p val, then update p's. If node val is smaller than p's val, then we need to go to the left, right? But if p left there is, then p equals p left. If not, go to the p next. Oh, but if we set to p's left, then we need to update the p counter of smaller equals to 1, right? And then go to left. Yeah. And if there is no, okay, I'll do it here. If there is no left node and smaller than it, then we just append it, right? So p's left equals to node. Yeah. And then the other case is bigger than it. Okay. When it is bigger than it, then when it's bigger than it, if there is right node, we go to the right. So if p is right, we go to right. Right? We don't need to update any numbers because it's bigger one. Yeah. Wait a minute. When a node is going down, I think wait a minute. We need to update the count of a node itself, right? The node may count of cell when we insert it, like left. We only insert to left when there is no left. So bigger than it, smaller than it. Okay, bigger than it. We only update the node tag when it is bigger than the p, right? So say node val is bigger than p, then here we update p count here, but we know update node count of smaller equal to p count of smaller plus p count of self, right? This is when it's bigger, so we update the count of node. And if there is p right node, we're gonna set p to p's right. And this will gonna be the next iteration. Yeah. And then if there's no right node, we append it. So p's right equals p node. P right equals node. So, and when we set pf in node, we break. And we need to return. Return what? Return the node count of smaller, right? Here, return node count smaller. I'm not sure whether this is right. Let's try. Okay, search and insert. This is function. This is root. Now, because the root is the rightmost number, of course, the result would be 0. And for I equals nums.nums minus 2, loop through odd numbers, and the result we just push search and insert nums I, right? And finally, here is we just passing the number. I'll wrap a note here. So return result reverse. Here is actually the val. We wrap it, node equals new node val. Yeah, this doesn't work, I think. Yeah. There's syntax error. Oh yeah. Ooh, it works. Really? Empty. Wow, it might work. That's beyond my expectation. Cool. So cool. Wrong answer? This is not right. This is not good. This is right. Until we get 8. That is not right. Let's wait a minute, what's the problem? Right. Until here we got wrong. Let's just pick the last numbers to just add some debug. So the error can become 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3, 6, 9, 10, 11, till 76. It seems that error comes, yeah, if there's only these kind of numbers. Cool. So the problem becomes here. 9 is okay. 51. 51 is cool. 99. 99. When we insert 99, there is some problem. Okay. Wow, it's hard to debug. What if this looks good? This is wrong. This is still wrong. This is wrong. This is right. So I can reproduce this. So let's draw some graph. First we have 66. there will be no duplicates, and then we have 84. Wrap it. This is the val, and p is the root, and then they're not the same. So it's bigger than it. So count of full motor equals count of motor plus itself. So 84. There's no right. So p right equals 84. And then count of motor updated to 1, right? Yeah, this is right. What we return. It should be it's not stable. Okay, this is right. Okay, so 1, right? The problem will become 99. Okay, now we got 21 smaller than it, so 21 here. Now 9 smaller, so 9, and 51 smaller than it, bigger than it, so 51. Now we got 99, 99 bigger than it, and so 99 is here. I know what happened. Yeah. We're at set. We set the count of smaller to the p is count of smaller. Let's just update it. So here, the smaller is 0, right? And now we add 84, smaller actually becomes 1. And then we got 21 smaller than it, so here should be 0, but we did update the node here, p is count smaller plus 1, so here I become 1. Right? You see, when we after insertion, the account doesn't, it's not updated anymore. So we need to sum this up. Actually, the sign does not work good. I see. So after 9, this becomes 2, 1, 0, 0. No, not 0, but 1 here. So it equals 1. I know what happened. I need to node count number. Need to sum up. Yeah, not the piece counts motor plus counts self. Should this work? We got one more. Wait a minute. Okay, let's just do this over again. What to return is 0, 1, 0, 0, 2, 5. 2, 6. Okay. So for 66, it's at beginning it's 0. We got 84, bigger than it, and we inserted to 66. Count of motor equals 0. Count of itself is 1, so we plus is 1. So it should be 1, right? And then we got 21. Move to the left. and here +1. Insert it, and yeah, it's still 0. Now we got 9. Insert it, update it, update it. Yeah, this is right. And 51, insert it. Go here, bigger than it. So 51 will have 1 plus itself 1, so +1, so it becomes 2. Right? Now we got 99. 99 bigger than it. And 99 will have bigger than it, so 3 plus 4 equals 4. And then equals this, right? And 84. Ah, there's a duplicate calculation. So actually, we're only counting numbers smaller than it, so this only works for the root, right? This root. If this only works if you're going to the right. So only the numbers in the left part is right. On the right, it doesn't matter. It doesn't work actually. So this one actually count this 666, and when we're inserting 99, we calculate it again. So number of smaller actually should only count the root, right? So count of smaller, and then only count the self. Count of smaller. Kind of smaller here. I think we need to count not smaller, but count the left tree, right? Count of left tree, plus it, and count of it, and plus left tree. So this is 0. I see. It's not smaller, but let's rename it count of left tree. Okay, so if it is self, we update the count of itself. Yeah, and we update when it's smaller. We update count of smaller node. We update left tree and return the node left tree. Yeah, and when we go into the right, we will count the left tree plus its count itself, right? So when we are going to 84, we know 3 plus then the count. Count of tree, count of tree. And then we should not return the count of tree, but we need to create a number which is let count of smaller 0. Okay. If it's the same, we return count of left tree. X left, update the p count of tree. Okay, and then p left equals p left, and they return, still return 0. And when we go to right, like here, every time we pass a node, we collect the left tree count and the self count. So this will be incremented with the count of left tree and count of self, right? Like this for 84. For 84 itself, the left tree is still 0, so we return, okay, 0 is the same here. So I think that's it. God bless. Yeah, nice. Hope we pass. Sad. Still not passing. Now we get it further. Well, actually, almost there. Why almost there? Is there still some problem? Maybe because duplicates? The error. Okay, let's try. Right, no problem. We can use BFS binary search for here to find the failing test case. Okay, this looks good. This looks good. What is this? Okay, looks good. Looks good. Looks good. Looks bad. Ooh, good. Randomly. Okay. So the problem is duplicates, I think. We handle. So we kept 23. It should be wrong. No, it's okay. So what's the problem? Okay. 33. 22. Right. 7. Wrong. 90. Wow, this is short enough. 23. Okay. So this is the case. Wow. What the? Oh. I think there's a major issue in my code. Well, even this? Okay, this is easy to go. What we return is last for 23. We return 0. If it equals to 8, we count off left tree. We update. Okay, let's see. first we get 22, count of smaller 0, selves 1. Then we got 52, as we did here, count of, we will insert it 52 here, 0, 1, right? But the count, we will return 1. Yeah, which is good. And now we have 23. 23 is bigger than it, but smaller than 52. So it's 23 here. When doing insertion, you don't update anything about no. So the smaller 0 count will be 1, and we return 1. Cool. And then we got 5. Of course, 5 will be inserted directly, and then we will update this smaller left tree. Oh, move to left. Here is updated, and then updated. 5 will return 0. That will get 23, bigger than it, and then smaller than it. So, I know what happened. We actually updated here to 2 and find 23. We find the same 23. The count would be count of smaller and that self, so 2, right? So here we insert to the left, return count of smaller. So it should be, and then return count of smaller, so 1 plus 1, 2. So we should return 2. Why didn't I return 2? Insert down. Insert 5, 0. Insert 21, 23, 1. Two, 23, 1, 5, 1, same, 23. 23. Wait a minute. 23, and then we now get 23. Shit. I know what happened. P count of left tree, and we'll plus the count of smaller. When I going from 22 to 52 and 4 in here, yeah, this is a problem. Wow, this should be a hard problem. God bless. Come on. Yay! Finally. Wow, this is very challenging, I think. So that's it. Let's analyze the time complexity. This, wow, for worst case will be, as we analyzed, this will loop through all the nodes, but the insertion actually will be constant time. So I think it should be in logN. Worst cases, quadratic, and the space. We created nodes, right? So it's linear space. Okay, so that's all for this one. Hope it helps. See you next time. Bye bye.